Welcome to this lecture series on cardiovascular physiology, and with using the textbook Human Physiology, an Integrated Approach by Silverthorne. Again, this originally is from the 5th edition, but we may continue to use it throughout. And we have this as the first lecture in the second module titled Integration of Functions, under which we'll cover the cardiovascular, respiratory, and renal systems. So this is listed as the Cardiovascular Physiology 1. Again, we kind of negate chapters in case they rearrange chapters in future years. Topics rarely change within chapters. And this will be the first out of what I've decided to split up into 3 portions for this chapter 14A. So hopefully by now you're beginning to appreciate how we follow through these. So there'll be a cardiovascular physiology number 1-1-2-3. And this first one will cover the introduction to circulation, the concept of flow, basically some of the physics, as well as for resistance. And then as we proceed, after talking about the heart and the vessels, in the second and third parts, then we'll begin to study how pressure and flow is generated within the system. And I guess I forgot to list pressure on this one, sorry. Did I put it there? Okay, well, introduction to circulation includes the idea of pressure. So we'll have the overview of the cardiovascular system, pressure, volume, flow, and resistance in this first one, cardiac muscle in the heart in the second, and the third will be looking at the action potential and contraction within a contractile cardiac muscle cell, and then we'll progress to the 14B, very likely a 1, 2, and 3 as well. I'll predict ahead of time now, looking at the heart as a pump. So as an overview of the cardiovascular system, we are reminded, of course, that it is for transport, and I like how the authors kind of review the evolution of circulatory systems, not necessarily, as well as cardiovascular. Remember, circulatory system doesn't have to have a cardio component, right? So some lower organisms simply use the movement of the body or the compaction of tissues associated with locomotion to mush the fluid, right, extracellular fluid, and ultimately create channels to direct that. And then as the organisms get larger and larger, and diffusion is even more so out of the question, even with the sluggish bulk flow created by compression of body fluids with locomotion, you have to introduce a centralized pump within the canals, and there can either be an open circulatory system where you've got a combination of the interstitial fluid being mushed and forced into the low pressure and the venous side of the cardiovascular system and then the heart continuing to draw it in and pump it out and keep the circulation going. And a big part of it, as we know, with the circuit is always going to be an external respiratory system. In the humans, we know that is the lungs, interposed between the output of the heart and the delivery back to tissues. And obviously some bathing along the pathway of the circulation for the absorption of the digested nutrients. So not only do we have it associated with the absorption, the gas exchange and the nutrient and waste exchange, if you will, it circulates the oxygen, nutrients, and water. And so in the humans we have a closed vascular circuit. The only site where we see the interchange of the plasma portion of the extracellular fluid compartment and the interstitial fluid component of the extracellular fluid compartment is at the capillary bed. And we'll talk about the anatomy of capillaries and relate pressures and flow to that interchange at that level when we get into blood flow and the control of blood pressure. And of course with the respiratory system and renal system we'll see it again. So now that we've kind of made that brief assessment of the evolution to a closed circulatory system, as in the humans, with the single four-chambered heart, and related it to the integration of the vascular circuits, the flow to all the cells here, of course, is the systemic. The blood flow to and through the lungs is the pulmonary, and then of course there's a GI, gastrointestinal circuit to the vasculature. So we'll describe these again as we proceed, and then even other subsets of flow like cardiac and cerebral to the brain, and so on and so forth. But for now, let's consider the circulation for the materials moved from cell to cell, so the wastes. So obviously we'll get to the discussion of the urinary system, but the GI system is also a site of the excretion of some, secretion of some, well, no, we really have to call it excretion, don't we? But anyway, the excretion into the GI tube, and then the loss, like bile, if you will. And then some cells will be the source of this, and then the liver will be responsible for some of the processing of many of the wastes. And as I just stated, the bile going into the gastrointestinal system would be the excretory part associated with that after the liver. So the immune cells and the antibodies and the clotting proteins are also components of the plasma component, subcompartment of the extracellular fluid compartment. They're present in the blood continuously, and they're available for any cell that needs them. The hormones, as we know already, are coming from the endocrine cells and are being circulated such that they can diffuse around as freely as possible, whether they are lipid soluble or water soluble, and bump into cells randomly, and when they bump into a target cell that has the receptor, or diffuse through it, as with a lipophilic hormone, and happen to encounter their receptor and hit it just right, then they have found their target cell. So again, that law of mass action, nothing has an intention and an intentional direction. It's all diffusion and random collision. However, remember, you can produce localized, concentrated areas by having a carrier molecule or a binding protein or a receptor, if you want to proceed all the way from the idea of a carrier protein in the plasma to a receptor in the cell. So I don't want you to think that hormones have an absolutely uniform concentration throughout all tissues and cells within tissues. The way that you can hold them in an area is to have them bind and release, so they can't freely diffuse away from that site. So it holds it there for a longer period of time. And as well, this helps us to understand how hormones, when they diffuse into the blood from the site of release, are held in the blood at a slightly higher concentration than in the interstitial fluid, and then that favors the diffusion away from the blood and at the capillary beds. So most hormones, as you recall, had carrier proteins in the plasma. So and that would fall, well, they're just saying clotting proteins here, but there's other proteins as well in the blood. The stored nutrients, of course, would be the molecules being circulated, liver and the adipose tissue we know well, and all cells benefit from the circulation of those. And the materials leaving the body, the metabolic wastes, are coming from all cells, the heat and the carbon dioxide, and of course the kidneys and the skin and the lungs are examples of the delivery or the sites of removal of these, and therefore we consider that the target for delivery. But just as it happens to be passing by in this closed circulatory system, we have an anatomical structure for filtration and reabsorption in the kidney to produce urine, and for the diffusion heat, the dissipation of heat, I should say, right, through convection, predominantly, as you know, and perspiration. So the lungs, as you know, for the gas exchange. So let's move on then to get a overview of the cardiovascular system. So the cardio, obviously the heart, and the vascular, the blood vessel, the tubular system. And we are showing intact capillary beds distributed throughout the illustrated cartoon-like organism here, and reminds us that it is a closed system. That means you can have pressure differential across the entire system. So from the heart through the aorta, all across all these capillary beds and the inferior vena cava back to the right heart, you have a complete pressure circuit that has a parallel one, that going to the the trunk and the rest of the body from the neck down, as you know, and then up to the upper extremities and the head, the higher level parallel circuits that will have a pressure gradient across the entire one as well. So we'll be talking about short tubes of vessels having pressure gradients. It's at this point we want to think of the output from one of the chambers of the heart producing an entire pressure gradient across the entire vasculature back to the site of origin, if you want to even think of it that way. And it's this pressure differential across the entire circuits that ultimately becomes really important, as you know, in cases where the left heart fails and the right heart still is very good at pushing blood into the lungs, but it can't get out. Then you can end up with pulmonary hypertension, and that's not a good thing. And with time, heart failure can ensue, as you might know, with leading to COPD, chronic obstructive pulmonary disease, and things like that, or congestive heart failure. As well, let's not forget local circuits, the cardiac circulation, the coronary circulation, coming. It's the first branch off the aorta coming out of the left ventricle, as you hopefully know, and you get the circulation there. So we'll talk about that when we get into the blood flow and the circulation. When can you get blood flow into the heart? You can't get much arterial flow into the ventricles when they're fully contracted. It's squashed everything. The muscles contracted so much. So it must be during the relaxation part that you then can get the flow in there. So what's the timing of all the events, the biomechanics, if you will, that allows that? Okay, let's back off then and get this at the introductory level. Now that we've talked about them, considering them as complete circuits, what indeed are the two major circuits of the cardiovascular system? Well, we know that there's the pulmonary circulation, and then the rest is the systemic circulation. And there's different components of the systemic circulation. The first we would consider would be the coronary, or the cardiac circulation, right? First one off the systemic. And then we will see, or if you take the comparative anatomy course, you'll see that the favored circulation is to the head and the upper extremities. So the cranial circulation, or the head and the brain circulation, is highly regulated, and as you might know, the brain has a very high metabolic rate and has a lot of influence over this, and can basically starve everyone else of blood flow to favor blood flow to itself. The two most important blood flows that have to be maintained are the heart, obviously, and the brain. Without either of those two, without the heart getting the proper supply, you can't maintain any flow to the brain. Without the brain, you can't be conscious. If you're not conscious, you're not living, ultimately, right? Your breathing and everything else shuts down, then that goes. Some of the most rapidly shut down circulations are the digestive, as you may know, and the renal. So these, you can see, are parallel circuits shown here, and even though we don't get into the resistance, the difference between resistance in series and resistance in parallel, these are shut down selectively, even some within the trunk, to maintain the blood flow through these critical regions during exercise and with sympathetic activation under those conditions of fight and flight. So the systemic circulation has basically the carotid, the ascending arteries as it's called here, but the carotid coming up to for the cranial circulation, and then the abdominal aorta branching from there and giving these different supplies, the hepatic, the digestive, and the renal, and then of course for the hind limbs and the pelvis associated with that. So many components of the systemic circulation, and we'll see each of these, even for the pulmonary here, we'll see them again when we go through that. And then of course the corresponding veins, with the two major veins, the superior vena cava and the inferior vena cava. And we will of course talk about those in the sense of systemic venous return. Systemic venous return, as you know, is deoxygenated, so right heart is deoxygenated, and that is sent to the lung through the pulmonary trunk into the pulmonary arteries. And so the output of the right ventricle is into the lungs. The venous return to the left side of the heart, left atrium as you know, is oxygenated blood. The return circuit from the pulmonary circulation, then the left atrioventricular flow is into the left ventricle for the high pressure chamber for the ejection into the aorta, and that will bring about the coronary circulation and the systemic circulation. So finally then, left heart is oxygenated, right heart is deoxygenated after birth, as you know, right? So with fetal development, there is a change to this complete closed circuit. Well, there's a pressure gradient, as we said, across the entire circulation, and this one is just considering it the entire systemic circulation. So if you were considering the measuring pressure right here, just at the root of the aorta, after the ejection event of the left ventricle, so what would be your peak pressure there? And then again, pressure on the common receiving side, so you'd pretty much have to be in right atrium to get both the superior and inferior vena cava coming in there. And of course the coronary circulation drains into there as well, but not contributing too much to the right atrial pressure. So we're considering that as the vena cava pressure. So there's a tremendous drop, as you know. The pressure being shown here, as we are trained to read our axes first, the mean systemic blood pressure. So there is a formula to use systolic and diastolic pressure to estimate the mean systemic pressure, and the units most commonly used are millimeters of mercury. Other units are described in the textbook, the Torr, and using water, column of water rather than mercury, but millimeters of mercury is the most common one that we are very likely to see. And I won't challenge you with any interconversions if they appear. We will make every effort to provide the conversion factor if you need to convert it. So in other words, if you see something and you see the value of Torr and the conversion factor isn't included in the text, very likely you're not going to have to convert it. So I'll try and do my best at that. Watch for it. So obviously highest at the aorta, closest to the left ventricle, and lowest at the vena cava. So quite often we look at graphs, but we don't stop and look at numbers. So let's look at this. We have a total pressure gradient, pressure difference, the low end at the vena cava, the venous return at the heart, the right atrium, is looks like it's about 5 to 8. So this is 20, so 10 would be there, so it's about here. So it's somewhere around 5 to 8 millimeters of mercury. And that's the mean. So we know that it will vary across that with the beating of the heart, systolic over diastolic. And the mean is about, it's got to be about 95 there, right? 90 would be here, so that's got to be about 95. So we have a pressure drop from about 95 to 5, so a total delta P of negative 5. So the change in pressure is a negative 5. We put the negative on there to show that it is a decrease over the length of this circuit. Well, now obviously we're going to start considering something that's similar to that, using glass tubes and columns of water, excuse me, to get a little bit better understanding about how pressure is distributed in columns of liquids within containers. So why is this an open container? Think about that for a moment while I complete this other statement. So what we want to do is consider it in physical containers and then transition it to the, here these are fixed containers, to the vascular container that, of course, as you know, can change in size. So we know that our vessels can constrict and relax, so we can change the size there. Be right back. The thing about then is what happens in a fixed container to generate these pressures. So hopefully in the dead air space there you had a moment to think about it. So what is the difference? Why start here and then transition to a system that can change its size? Well, as you know, liquids, water-based liquids can be compressed to a limited degree. You can't compress water quite the same as you can gas, air I'm talking about, not gasoline. And hydraulic fluids have their own compressible characteristics such that within a closed container you can generate pressure. So there is a certain pressure within here. The pressure has not been released. As you know, pressure can be released. And the farther down in a column of water you get, the more water is on top of you pressing you down. Same thing with the air pressure, as you know, at sea level you have a larger column of air on top of you pressing down onto you than if you were on top of Mount Kilimanjaro, right? So the density of the air is even different because the gas compresses more so than liquid. However, at the bottom of the ocean, the water is more dense than at the surface because you're talking about such a great distance. So let's move ahead then here. What we are seeing is that we have 4 tubes. One tube is of the largest diameter and the other 3 are smaller. We only say smaller because they are each equal, so the diameter of these, that number, is only compared to this, the largest diameter, because it's compared to the other 3, right? But numerically, this number is larger than the number that is the same for these 3. Sorry about all the grammar there. Anyway, kind of like your multiple attempts on exams. If there's only 2, you get the larger toward it. If there's more than 2, you get the largest, the highest score, rather. So the hydrostatic pressure is the pressure exerted on the walls of the container by the fluid within the container. The hydrostatic pressure is proportional to the height of the water column. So if you, did you think of the answer of why we have this as an open system compared to the cardiovascular system? That's right. The source of pressure is the compression of the heart. So in the closed system, you have to have a source that is going to compress the liquid and create a pressure within the contained system. Well, if we use this model then of the open system and we completely open it so we don't have a circulation, we just have a draining, we can see a similar type of a thing of the drop in pressure as we get farther away from the source of the highest amount of pressure. And what this is going to do, because this is creating the highest pressure that has the greatest diameter of all four, it is going to generate pressure pushing against the air column on top of the water and the column of water, greatest at the column closest to it, and that will decrease as the column gets away from it. So obviously over distance that pressure is dissipated. Some of the pressure, the greatest amount of pressure by this column is dissipated here, and then more is there, so there's less left over to impact this one. So the farthest column is going to drain first. So what we are thinking about here all along, as we're seeing different sized arrows, is that pressure can differ over distance. So as we continue with our conversation about this, we'll be considering length as a factor in dissipating pressure. So there's an original pressure, and then it is dissipated by movement, and as well with the friction against the wall of the system. So once the fluid begins to flow through the system, the pressure falls with distance as energy is lost because of friction. So that's the situation in the cardiovascular system too. So the pressure change then is associated with the pressure created by contracting muscles, and that is transferred to the blood. The driving pressure for systemic flow is created by the left ventricle. So rather than air pressure, atmospheric pressure pushing on top of a column of water, as well as gravity pulling it down, right? We now have a closed system with a driving pressure that is a pump, the heart. If the blood vessels constrict, blood pressure increases. So you can increase pressure by decreasing the volume of the container, or the size of the container, and trying to compress trying to reduce the volume of the fluid contained within it, and the resistance of the degree of compressibility of the contents, the blood, will determine the pressure change. If it easily compresses, it's not going to build a big pressure. If it doesn't like to compress, it's going to create, a bigger pressure. It's going to push back onto you as you're trying to press it down into a smaller container. And they use water in a balloon in the example in the textbook. So if the blood vessels dilate, blood pressure decreases. This is what we want to think about. So obviously the terms that you should be familiar with and will need to be even more familiar with is the contraction and dilation of blood vessels. If you get a contraction of the arterioles in the blood vessel system, you're going to get an increase in the systemic arterial pressure. So you note now that I'm adding specific terms to what pressure we're talking about and what vascular bed. So that becomes very important because the cardiovascular system is complex, as we just saw. And to give it away right now, we'll go right back to it. This input, the smaller, the precapillary portions of the arteries, and they're called, as you know, arterioles, then precapillary arterioles, is the most important site for contraction or constriction to shunt blood flow from capillary beds, and then closer to the heart, more proximally, you get constriction to regulate regional flow. And these are predominantly the resistant vessels at this level. So if you contract here, then not so much blood can get through here, and you have more volume here in the same size container back here. but overall you have reduced the size of the container. So we don't contract the entire circuit, arterial and venous side at the same time. There's differentially distributed contractions, but anything you change anywhere, because it's a closed circuit, affects everything else. So again, we're going to constrict here, and constrict here if we need to favor circulation to the pelvis, trunk, and of course the arms and the head and the brain. So this is the idea that we're working on at this point when we're thinking about vessel constriction or vasoconstriction and vasodilation. So the volume changes greatly affect the blood pressure in the cardiovascular system. So if somebody hemorrhages, they become hypovolemic. Hypo, as you know, is down, and ic refers to the blood or a condition. Sorry, not to blood, but to a condition. And so their blood volume has decreased. If the size of the container does not decrease, then blood pressure is going to drop tremendously. And so there are limits to the degree to which the vascular system can contract and reduce its overall size. So if you hemorrhage a little bit, the body can compensate and keep your systemic pressure up enough for circulation to your critical organs. You lose too much, and no matter how much you get of a vasoconstriction, you just can't keep the blood pressure up. Now there are other components to the blood pressure overall, but right now we're just trying to think about the volume of the container related to the volume of liquid within the container, and how pressure is generated, and especially changes in pressure, because without a change in pressure across the distance, we're not going to get any flow. So if you have a straw full of water and you're not blowing on it, there's no pressure differential, you're not going to get any water flowing. But once you blow on the straw, or if you want to say air within there, once you blow on it, then you get a pressure differential, a higher pressure where you're blowing in and a lower pressure on the other end where it's escaping. So fluid flow through a tube depends on the pressure gradient. So flow dynamics is a very sophisticated and complicated mechanical system to study, and the mathematics are quite sophisticated. But when it comes down to it, there are some very simple parameters that are the most critical ones, especially for a biological system, especially at the introductory level. So the flow and pressure relationship is very important. So it's at this point where we remind ourselves that this alpha symbol means related to. And if the number here, if the the value here is in the numerator, then we say it is directly related to. And as you know, if it's in the denominator, 1 over, it'll be indirectly related to. So we're going to build on that, and hopefully you remember this system. So flow is directly related to the change in pressure. And the change in pressure is the pressure differential across 2 points along the length of a closed system, a closed container within which you can generate pressure. It can be open on 2 ends as well, as long as you have some way of some drive and some release. So if the higher pressure is on one side at P1 and the lower at P2, then you have a pressure differential with a value. In many cases, you will be well, anytime you're talking about a pressure differential, it's a drop in pressure. But if you're measuring, if you want to know the pressure differential at this end, you would have a negative value. If you wanted to know the pressure differential at this end, you'd have a positive value. Does that make sense? So what is the pressure differential on the input side versus the output side? It's 5. So it's 5 greater here than here. What is the pressure differential on the output side versus the input side? It's a -5. That means it's lower here in the output than on the input. So here we see 100 millimeters of mercury on the input on the left side and 100 millimeters on the right side. And so if we asked what's the pressure differential on the right side versus the left side, there is none. And what about the left side versus the right side? There is none. Okay, so if there's no pressure differential, pressure gradient, then there is no flow. However, if you do have a differential, 100 millimeters of mercury on the left, 75 millimeters of mercury on the right, obviously that's a 25 millimeter difference. So it is a -25 millimeter delta P on the right versus the left. And we see that we have two different pressures, 40 versus 15 on the left and the right here in the lower tube, but the delta P is actually the same. So the pressure differential on the right versus the left is a -25 millimeters of mercury. You're going to get the same flow. So we now begin to ask ourselves, well, what do you mean? What does flow mean? Is it how fast it's moving or how much of it is moving? And of course, this is flow in the sense of how much is moving. So what's the volume that crosses this point? So if you're standing here making your observations, you know that you've got a -25 millimeter delta P relative to the input. And your device can measure the volume of fluid passing over a certain distance in front of you in a period of time. So that's the flow. The volume flow is what we're talking about when we say flow here, not the rate. So if you think of this as blood, now think of following a single red blood cell as it passes in front of you. How fast does it go through the same distance that you just measured the volume? And that's going to be the flow rate or the velocity of flow. So think of these. Be careful when you hear about flow and ask for specifics. Do you mean volume or velocity? And you got to do that because it's a big difference. So here, when you look, we're talking about volumes. So one of the first things you see is volume and radius. So we're talking about flow in the sense of volume flow. So as the radius of a tube decreases, the resistance to flow increases. So the textbook goes through this very nice thing of talking about the parameters that are involved in determining radius. And we're summarizing it here. And they talk about using a small cocktail straw versus a large straw that you... large diameter straw that you might get for a big giant Slurpee McDonald's soda or something like that, supersized. You're obviously with a lower pressure gradient, you're going to be able to get more flow through a larger diameter straw. At an equal pressure gradient, so the very center point of these two exit pipes from this should be at exactly the same level. So that the column of water, the total column of water distributing the pressure equally in every which direction is hitting it right at the same central part. So the entire cross-sectional area here has the same amount of pressure pushed on it as you would with the entire cross-sectional area here, so that you have a uniform drive to create the flow. In other words, to create a certain pressure here, that would be that have another pressure here. So you've got a pressure drop across these pipes over that distance, remember? So we're assuming the same pressure drop, and all we have is a change in the diameter. And so we ask the question, what will be the effect on the volume of flow, or just the flow? So we have to think of resistance first. So resistance is indirectly proportional to the radius to the fourth power. Or we would say resistance is proportional to 1 over the radius to the 4th power. But when we see that it's the inverse on the right side, we say that it is, this means inversely proportional to. So this value this symbol just means proportional to, and then the arrangement on the right side, as you recall, determines whether you say directly proportional or inversely proportional. So resistance is inversely proportional to radius to the 4th power. So if we say that tube A has a radius of 1, sorry, I should be pointing to the denominator, 1 to the 4th is 1. So the resistance is, now we're saying this is approximately 1. And in tube B, over on the right side, the radius is 2, so 2 to the 4 is 16. So a doubling of the radius is going to decrease resistance by a factor of 16. Now we need to remind ourselves that flow is indirectly proportional to resistance. And what you should be doing right now in your mind is taking this 1 over radius to the 4th and this resistance, and making the flow, inverting this whole thing is resistance, and then this is 1 over flow. So 1 over flow is proportional to 1 over radius to the 4th. And so and then of course you can just invert that and say that flow and radius to the 4th. So if you increase radius, then the volume flow is going to increase. If you increase radius, you decrease resistance. If you come over here, if you decrease resistance, you increase flow. So however you manipulate these in your mind to make those associations between radius to the 4th power and flow, or if you just memorize that as you increase radius, you increase flow, it's fine. But let's now apply this, the relevance of this to the power of 4. Obviously, if the resistance is 1, as we had estimated here, the flow is going to be about 1. And these don't necessarily, we're not saying units, and we're not saying necessarily that that's the absolute flow here. We're just saying that this could represent it. And we simplify it so that it would be that way. So 1 over 16 is 16. So hopefully these simple mathematics are coming back to you if you haven't done them in a while. So the flow would increase by a factor of 16 with a doubling of the radius. Difference here. So we'll come to the box and then back to this. But first, let's look at this very important formula that is shown above here. So a typical thing in physiology is to have a word equation or even a sentence description and then a word equation, then a mathematical equation that will emerge through this process. So different ways of describing the biophysical properties down to the point of being able to say V equals Q over A and putting numbers in there for what values you do know and calculating the unknown, right, variable. So very standard stuff, but this is the really important one in the end. Mean arterial pressure is proportional to and directly proportional to cardiac output, and it is also directly proportional to peripheral resistance. So if we separated these out and saying what's the relationship of this MAP to CO and to PR as two separate equations, we'd have one that would say MAP is directly proportional to CO, and then another one, MAP is directly proportional to PR. And usually it's TPR, total peripheral resistance. So the entire systemic vasculature resistance is what we would have to be thinking about. So MAP then is also proportional to, directly proportional to CO times TPR. And we'll revisit this, obviously, as we proceed. So I told you that one way of calculating or estimating mean arterial pressure was systolic over diastolic. So there's a formula for that. So you could know this, and you can measure cardiac output even in humans with echocardiography and a few other type of techniques, and research methods are available to get very accurate measurements as well. So if you can estimate mean arterial pressure and cardiac output, what else can you what can you learn from that? You can calculate total peripheral resistance. So this is an introduction to what we will be encountering, and certainly there will be some exercises and case studies where this will be relevant. And these will get added to the course for you to expand your knowledge and understanding and apply this information. So we'll build on this more after we have looked at a lot of these other relationships that flow through the heart. Let's now think of it in the sense of velocity equals the flow rate over the cross-sectional area. These all become very important if you think of cardiac output. So there'll be a direct application of this to the cardiac output, because the ventricle, it's not going to be tubular like this, but when it is filled completely, it's going to look like this. When it empties, it's going to progress down a change in the cross-sectional area until it's fully contracted. Right? So as you reduce this and create a pressure, and this is going to increase, then the velocity will reach a very high level. And if you're thinking of it calculus-wise as the changes, so as you get the delta A, right, as this decreases. As the rate of the decrease in this increases, then the rate of the increase of the velocity is going to increase tremendously as well. So remember I said the rate at which this decreases with the contraction of the ventricle. So I know this is making many of you think, what is going on here? You have to start thinking about these things to apply these equations to the cardiac output. What we're starting with is a simple set of tubes, and we'll proceed to trying to appreciate what that means with cardiac output and the velocity at which it can empty over a certain period of time, such that it does empty. If it doesn't empty over that period of time, if something changes the whole dynamics of this for the left ventricle, and then it doesn't empty all the blood that it received from the pulmonary circulation, you begin to have heart problems, and that can lead to ultimately to congestive heart failure. So we're very much at the superficial level. So let's think about how this interrelationship of diameter. Remember, do you remember how to calculate cross-sectional area? Well, obviously radius and diameter are going to be very important. We won't get into it, but so the diameter is what we're talking about here. Is the diameter of this tube is greater than the diameter of this tube. If the diameter is different, then of course the cross-sectional area is going to be different. And we're ignoring for now the formula for a cross-sectional area, but recognizing that diameter is going to be a key factor in determining the cross-sectional area. So here at point X, we have a cross-sectional area of 1 centimeter squared. And at Y, we have 12 centimeters squared. The volume of liquid that we are considering flowing through this cross-sectional area is 12 cubic centimeters, cubic centimeter. 1 cc is roughly an ml, if you remember that. So we'll end up converting this to mLs of blood, but for now, just think of it as water. Cubic centimeter is a typical volume that's used. The flow rate, Q, is the volume over time, right? 12 cubic centimeters per minute. So let's look at the formula here above. So at point X, you have the velocity equals 12 cubic centimeters per minute over the area, cross-sectional area, the 1 centimeter squared. So these two disappear, and that becomes just centimeters, centimeter to the first. So you get 12 centimeters per minute. And then at point Y, you have 12 cubic centimeters per minute over 12 centimeters squared, and you end up with 1 centimeter per minute for the velocity. Started off, I had told you that we would think of this as having the velocity be the same across here, and stated that you would have to put a larger volume of blood into this smaller tube to keep that velocity the same. That's the reverse of what is being shown here, which is really the more common condition, in that you have to have the red blood cell move faster in the input to get the same volume at the output.